Hello, physics class. Today's lesson is going to be about gas laws and a little bit about how physics works. The reason that I want to go over gas laws in the context of how physics works is because there's a few equations and they might be a little overwhelming or confusing, and I'm hoping to kind of build a box for you to keep them in. So here's the first thing you need to do if you're going to do physics. You need to assume that math works. Math works. All right, let's move on. If math works, then we might also note that the universe is mathematical. That's something that is pretty awesome, if I might say so myself. But if you take those two together, assume that math works, and then also that the universe is mathematical, you get to this. You can write equations that correctly describe the universe. That's what physics is, or at least the approach that I'm taking to it here. Physics is just the investigation of the universe in a way that leads to equations that correctly describe it. The purpose of these equations is so that you can not just describe the universe, but also predict how the universe will be later, and that can be very helpful to us humans in the universe. Okay, so basically what this means is that any math tricks that you know are basically also universe tricks. So there's just one math trick that we're going to use today, and it's something that you probably learned way back in like 6th grade. This is really not too difficult. We're just going to be talking about direct variation and indirect variation. And it is as easy as your favorite first semester physics equation, D equals VT. Direct variation has to do with two variables who change in the same direction, assuming that everything else is constant. So here's a good example. Distance and velocity vary directly with each other in this equation. The idea being, if your velocity increases, as in if you travel faster, then your distance should increase. You should travel farther. That's direct variation. Indirect variation is, well, it's the opposite of that. And the two variables that vary indirectly here would be velocity and time. That is, if you go faster, you can cover the same distance in less time. So, all of the gas laws that we're going to do in today's lesson are going to be an exercise in direct and indirect variation with a constant thrown in where it's necessary to make everything match units. Got it? All right, then let's go. Well, if we're going to have equations about gases, we need to have variables, and if we're going to have variables, we need to have measurable quantities. So let's just list some of the things that we could measure about a gas. First thing we could measure is, say, how much volume it takes up. All matter has mass and takes up space, but gases in particular, one of the most interesting things about them is that they expand to fill space, so the volume is a pretty important fact, characteristic about a gas. Let's see, what else? We've also got pressure. You hear about air pressure a lot, particularly if you go to different elevations and you've got low air pressure up in the mountains, or if you're driving a car and one of your tires is low. So volume and pressure. Something else that you can measure about any substance, but it's related to these, would be temperature. Of course, the temperature is going to matter because we're dealing with a gas that can expand and contract when its temperature changes, but also because we just did a unit on heat exchange, and don't you think that's going to come in handy? Okay, so volume, pressure, temperature. Something else that you can measure for all substances, you might think mass. And while that is true, turns out what's more important for a gas is not the mass, but in fact the number of particles. However, because molecules are so tiny, it's not really practical to measure the number of particles, so instead we measure the number of moles. Those are all of the different things that you can measure. Now, it's been known for quite some time, ever since the development of stoichiometry, which hopefully you remember from chemistry, that 1 mole of any ideal gas occupies 22.4 liters of volume at what's called STP. STP stands for standard temperature and pressure. Sorry that writing got a little messy. I was afraid I was going to run off the edge of the frame. So standard temperature and pressure is STP. What is standard temperature and pressure? Well, the temperature would be 0 degrees Celsius and the pressure would be 1 atmosphere. In other words, just a cold winter day. Okay, so we've got variables. We've got some conditions that the universe brings to us. Now we want to do some physics. That means we're going to write some equations that accurately describe the universe. And we're going to do so only using direct variation and indirect variation. So we could ask something like, what do you think about P and V? Is it that they both change the same? Or is it that they change in opposite directions? Just think about it for a moment. Pressure has to do with the sum total of force that the particles exert on a surface divided by the unit area. So think about the air inside of a balloon. I'm going to draw a really terrible looking balloon. Yeah, sure, balloon. Okay, so there's particles of air inside of it and outside of it, but let's just focus on the particles inside. They're all randomly bashing into each other and into the surface of the balloon from the inside. In other words, they are exerting a force. If you take that force and you divide it by the area, you end up with a pressure. If this balloon expands, will that cause the particles to push harder or with less force on the walls of it? Well, I think it should be kind of intuitive to you that if you expanded the balloon, yep, really batting a thousand. I can't even say that figure of speech right. Batting 1,000 on these drawings here. If you expanded the balloon, the particles would have more room in which to run around, which means less collisions, which means less force exerted. So when the volume goes up, the pressure goes down. That would be not a direct variation, but an indirect variation. Now, if I just pull back that last that last page for a second, you'll notice that in the equation, the two terms with indirect variation are multiplied together, equaling a constant. Which means if I want to express that volume and pressure change in opposite directions, all I need to do is write an equation in which they are multiplied together. But then they need to equal a constant. The constant in this particular case is just going to be itself. So I can have the pressure as it started, that's the initial pressure, and the volume as it started. That would be this balloon. That must not change. We've got the final pressure, which has gone down, and the final volume, which has gone up. Pressure and volume change in opposite directions. It's an indirect variation, and this equation just says mathematically what I just said in English. When it's written down like this, we call that Boyle's law. There's your first gas law. All right, let's try another one. Okay, so we got an equation that had two variables, but there were a few others that we wanted to account for. So now let's do one involving temperature. Let's say you took that balloon. I got to draw this again. Let's say you took that balloon that you had filled with air, and for some strange reason, you decided to put it into the freezer. If you've ever put a balloon in the freezer before, then you know what happens. If you haven't put a balloon in the freezer before, look, I don't know what to tell you other than I'm really happy for you, and I hope that you enjoy your perfectly normal life. However, if you were to take that balloon and put it in the freezer, if you look at it later, you might discover a relationship between temperature and volume. Is it that the temperature goes down and the volume also goes down? Or is it that the temperature goes down and the volume goes up? Do you think a balloon will shrink or expand in the freezer? I think just common experience should tell you things tend to shrink when they get cold, so that would be a decrease in volume. Poor little shriveled balloonie. Okay, so if that's the case, we have a direct variation between volume and temperature. Now, if you'll remember our example, D equals VT. For direct variation, the two things that had direct variation were on opposite sides of the equation. However, if you were to solve for T in this situation, you'd end up with this. And so we have two different ways of expressing direct variation mathematically. They could be on opposite sides of the equation, or they could be on the same side of the equation, but in a fraction. We're going to go with this one because it's a lot easier to write from scratch. I'm just going to put the velocity and the temperature, the volume and the temperature in a fraction form. And if these two have direct variation, just like in the last one, P times V stays the same. In this case, V divided by T would be the same. And just like last time, what it's going to stay the same as is itself. It has an initial volume, quite large, and an initial temperature, quite normal. Afterwards, it has a much smaller final volume, much smaller, and also a much smaller final temperature. Now, just so we are clear, because fractions introduce a level of complexity a little bit harder maybe to understand, you can think of this almost like taking a fraction and putting it into lowest terms. Like, let's say that initially there was a volume of, say, 30 milliliters. At the time, the temperature was 20 degrees. Oh, you know what? I'm sorry. I should be using kelvins here because if I end up with a negative temperature, I'm going to have a negative volume. That's impossible. Use K, not C. Let's try that again. Let's say we had a volume of 30 milliliters at a temperature of 300 kelvins. That's really, really hot, but I'm just trying to make the math easy. If you put that in a freezer so that its new temperature is only 200 kelvins, well, this equation shouldn't be too difficult to finish. The final volume should be 20 milliliters. That's the idea. Okay, so there's a way to combine all these, and that's going to be next up. Okay, so let's put together everything that we've done so far. We've established that pressure and volume are indirectly variant, so that means that they should be on the same side of an equation. We've also established that volume and temperature are directly variant, which means that they should be on different sides of the equation, unless you want to put them on the same side, but in a fraction. We can actually write one equation that has P and V on the same side, and T on an opposite side from V. This is a pretty basic equation right here, and we're almost all the way to describing everything, because we've forgotten one of the quantities that we said that we could measure about a gas. If you remember back from our first page, we forgot about the number of moles. So, out of here. All right, so if we want to put the number of moles in here, that's going to be directly proportional to the volume as well, because if you've got more particles, you need more room to put them. So the number of moles is going to go over here somewhere. And now we just run into the problem of units, because if we're going to be measuring pressure, we're going to be using a unit called pascals. If we're going to be measuring volume, we're going to do that in liters, because this is a gas. If we're measuring temperatures, we also need to do kelvins. Number of moles doesn't really have a unit; it's just a number, unless you want to consider moles to be the unit. And that means that in order to make this work out mathematically, to match all these units that we've invented, we need to stick a constant in there. We call that R. So for your reference, R is equal to 8.3145 joules per mole Kelvin, and it is called the ideal gas constant. It's called the ideal gas constant because this equation, the ideal gas law, I rearranged the letters to show you how it's usually written, does not describe every gas in every situation. There's a lot of assumptions. It assumes that there are basically infinitely many particles that have like no size and they don't interact with each other at all. That's what's meant by the term ideal gas. This is a complete idealization, but like we've been doing physics problems without friction and air resistance for months and you never complained. So we're going to just treat gases as if they're like this. Air is pretty close to this. There are some gases which are not like this like at all, but we're just not going to do them in our high school physics class. So this is the equation that describes the behavior of pretty much every gas that we need to worry about. Pressure, volume, number of moles, that is that constant right there, and then a temperature in kelvins.